When you form a quadratic, we got in GCSE even, we looked at, oh, there's no real roots. There's no solutions. We did, yeah. Remember, you got a quadratic here. Oh, there's no solutions. Oh, no, there's no solutions, no roots. Oh.
Now we can just...
Now they're not just real numbers, not on this real axis. They're on a complex plane. Okay, now one way, so when we do like quadratics, for example, and you do the minus b formula, the quadratic formula, when you do that formula, you come to a stage where it might be minus 6 plus or minus the square root of negative 2 all over 3. And you go, oh, but now we know that that's negative 6 plus or minus root 2i over 3, don't we? And now we can continue. Yes?
I'm pretty sure we've done this in class.
Yeah, this would have been this. You would have done this with Mr. Gide.
Yeah, pretty sure about that.
Yeah.
But how do you know that's
Oh, because root, negative root. Okay. I did it. Okay.
This is all video.
Yes, on video. No, she didn't get it. People at home. All right. So that's. Now we can find all the roots. It's great. Also, we should recognize that these complex roots come in pairs, don't they? That once we know that the plus is a root, we also know that the minus is a root. It's conjugate. And we saw that geometrically when we drew them. You started telling me, oh, if we had a root over here, the other one, that's also a root, yeah? It was, oh, if we had something like this was root 3 plus I, then we know, oh, well, root 3 minus I is also a root. They come in those complex pairs because they must multiply to form something real. Anyway, the product, remember the product and sum of roots? Remember we did that? The product of sum of roots ends up being a real number because they come in conjugate pairs. And the conjugate pairs loosely come from this kind of, in quadratics definitely come from this. But you know, in quartic, for instance, x to the power 4, it would be 2 of these, wouldn't it?
Yeah, you would find 2 different factors, and then you would be able to find the roots of those.
Which was that question 7 we were looking at? You were looking at.
I didn't quite get it.
When I did it, and the whole thing is you found a bunch of roots. So you know that it was like 1 over root 2 plus 1 over root 2i plus minus, something like that. That was 2 of them. And 1 over root 2 minus 1 over 2 plus minus 1 over... I think that was it. So what you do is you to form the quadratics that made the Z4. This is question 7 from the homework 2 nights ago. You do sum and product of these roots to form the quadratic, which was z squared minus root 2z and so on. So you found this, and the b and the c, because they're both over 1, and then you did sum and product of this, and then multiplied them together. So that was your question, Hisham.
That's how you do that.
Yeah. Anyway, so we have these pairs, and then we came to roots of unity, and the square roots of 1, we already knew. We knew that would be plus and minus 1. Let's just look at plus and minus 1 on a quick Cartesian plane, here and here, yes? Through.
1 and minus 1?
Yeah, is that okay? No?
Yes. But isn't it an
Oh, yes, thanks. Yes, you're right, yeah. Not a Cartesian plane, sorry, an Argand diagram. We did z cubed as well, and we got a bunch of roots. There was a couple of ways we could write it. We could write it in polar form, or you can write it in Cartesian form. I think the polar form was like, we got 0, we got cis 2 pi on 3, and cis negative 2 pi on 3 or 4 pi on 3, depending on which way you went around. If you kept going positive, or you the same position. Anyway, I just want to plot those. I'm just looking at a quick plot. So this is 1. Sorry, this is 1, and this is 1. This is 1, and this is 1. Then we did Z4. We found all these roots, and these roots were conveniently positioned here, 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 and here. They were, that's in polar form, but this one I could put in Cartesian form very easily. 1, -1, I, and minus I. We found that. We did that the other day. Okay. I think we also did Z6 at some stage, did we? Or did we do Z6 equals something different? Well, we did 64, yes. No, we didn't do Z6. Okay, we'll look at these, and then we'll try and predict where Z5s will line up.
I imagine one of them will be on 1.
Yes, so Z5, one of them must be on 1.
And I imagine it's like 2 pi over 5 away from 1.
Sorry, this should be 1, not 0.
It's just one. It is.
Well, no, it would be like cis of 0s.
Okay, so what are the degrees going to be?
There's going to be one that's
Divided by
2 pi over 5.
Yeah,
It's just-
divided by 5.
You're going to divide it by 5, aren't you? Because 1 is always the starting point. Now, with other complex numbers, and you multiplied, 1 was never or was rarely the start. You ended up starting here, and then you figured out how far you have to go each time. This one's very obvious because 1 is always our starting point. So we always know 1 is a root of, this is Z. We're looking at Z5 is equal to 1. So this one would be here. We know exactly what the argument's going to be. 72 degrees, or
5 pi over
2 pi over 5, yeah.
Upside down.
So 2 pi over 5 is going to be here. And every 2 pi and 5 we're going to get one, aren't we? So there's going to be one here, one here, one here, and one here. Something like that. That mightn't be perfect, but you can see there's 5. And I know that each of them will have a modulus of 1 and an argument 2 pi on 5 greater than the previous one. Yeah? Okay? And that this one will be the complex conjugate of that one. And this one, and these ones will also be complex conjugates. Yes? Because when we do get a complex number, its conjugate must also be a root. That happened here and here. It also happened here and here. It happens here, 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 and here. And the sixth one, which we did something with Z6, but it wasn't 1. I thought it was 1. It was 64, you're right. If we start here, where are our roots going to be? We're going to have one here, 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 and here. Is that too many? No, that's too. That was Z7. Sorry. Yeah. I wrote 7. So we've one here. And then we have to do, okay, 2 pi divided by 6. So every pi on 3, we're going to get one.
You drew them all right, sir. It's just that there was that one on the bottom that should.
This one?
Yeah.
Yeah, this one, this one, this one, this one, this one. I put in that one and that one. Oh, yeah. I put in.
Put one down.
I got myself confused, yeah. This one, this one, this one, this one, this one. That's Z6. Okay?
And the one on the right. Yeah.
Oh, yes, that was the one is always. One is always a root of, and we know that. Like, what's the 6th root of 1? It's 1.
Oh, I just understood.
Good.
The argument.
Yeah, so so you got 2 pi. It's got to go round once and then divide by.
The increments are pi over 6.
Yeah. Pi over 6 is not. It's
Not that one, it's
pi
pi over 3.
over 3. Yeah, it's 100. Yeah.
Because
Yeah.
the full circle is 2 pi.
Yeah. Okay, he got it.
Shit, guys. That took me way too
So
long.
everything is brought from complex numbers? That's the byproduct.
Yeah, so complex numbers now is the answer to the fundamental theorem of algebra. We have that number of roots when the power is that, even with something as simple as this, which we only thought there was only ever one solution to. No, there are 6. And they come in complex pairs, the conjugate. Or there might be 2 real solutions here, 1 and -1. That's okay.